Hey coders, welcome to Code Tech Chronicles. I am Shashi Devendra and today we are diving into fundamental data structure, the linked list. Linked lists are everywhere, from how operating system manages memory to how your music player tracks songs. Like arrays, linked lists don't rely on continuous memory. Instead, each element called a node holds two things, data and a link to the next node. This structure allows them to grow and shrink at runtime, making them perfect for applications with frequent insertions and deletions. Let's get it started. A singly linked list is the simplest form of linked list. Each node contains a piece of data and a pointer to the next node. The first node is called a head and the last node points to null, indicating the end of the list. Operations like insertion at the head or tail are quick, but finding an element means starting from the head and traversing forward one node at a time. So if you only need to move in one direction, a singly linked list is an efficient and simple. A doubly linked list goes one step further. Each node has not one but two pointers, one pointing to the next node and one to the previous. This allows bidirectional traversal, which makes it easier to move back and forth through the list. Perfect for a use case like browser history, undo redo features, and music playlists. Of course, there's a trade off. You use more memory because of the extra pointer, but you gain flexibility. Here is a diagram of singly linked list and doubly linked list. Singly linked list shows the nodes connected one way from head to null, while doubly linked list shows nodes with both forward and backward connections. Let's break down the core operations you will perform on linked lists. These are your bread and butter in coding interview. You can insert a new node at three key positions: beginning, which is head, in middle after the given node, or at the end, the tail. What makes linked list powerful is that unlike arrays, you don't need to shift elements to make space. You simply adjust a few pointers and your new node fits right. So starting with the first operation, to insert at head, update the new node's next position, next pointer to point to the current head. Then update the head to the new node. To insert at the end, traverse to the last node and set the next to the new node. For deletion, you don't remove it directly. Instead, you bypass it by adjusting the previous node's pointer to next node. In singly linked list, it means you must know the previous node to delete the target node. For example, to delete the second node, set the first node's next pointer to the third one. In double linked list, deletion is even easier. You navigate backward using the previous pointer. For traversal means visiting each node one by one, starting from the head and using the next pointer. It's similar to reading a storybook, page by page. This operation is crucial for performing tasks like counting nodes, printing values, or even debugging linked lists. For search operation, searching in the linked list is a linear operation. You begin at the head and compare each node's value until you find the target or reach the end. The time complexity of such operation is worst case on, since you may need to check every node. So the tip is use traversal techniques efficiently to optimize logic during the search operations. Final thoughts: these four operations, insertion, deletion, traversal, and search, are the foundation of everything you will build on top of the linked lists. They rely heavily on pointer logic. Mastering them strengthens your understanding of how memory and data structure truly work. Let's talk about these four operations on linked list. Insertion: you can insert a node at the start, middle, or end. No need to shift elements like in arrays. Deletion, remove the node by updating the surrounding nodes pointers. Traversal, start from the head and follow the next pointer to visit each node. Search, check each node's value during the traversal until you find your target. These operations rely heavily on understanding pointers, and they are excellent for building your fundamentals. Okay, one of the most common in interview question, how do you reverse a linked list? You can do it iteratively by maintaining 3 pointers, previous, current, next, and flipping your direction of each next pointer one by one. Or you can do it recursively by letting the recursion reach the end and then reversing pointer during the return phase. Iterative reversal is on time and on space. Recursive reversal uses on space due to the call stack. Either way, it's a great way to test your understanding of pointer manipulation. Now let's talk about one of the most elegant and widely used algorithm in data structures, Floyd cycle detection algorithm, also popularly known as tortoise hare algorithm. You use 2 pointers to traverse the linked list at different speeds. Slow pointer, the tortoise, moves one node at a time. Fast pointers, the hare, moves 2 nodes at a time. Now here's the magic. If the linked list has no cycle, the fast pointer will eventually hit the null, reaching at the end of the list. But if there is a cycle, the fast pointer will eventually lapse the slow pointer and they will meet at some point within the cycle. Why it works? It works because the difference in speed. Think of it like a circular racetrack. If you walk and your friend runs, eventually they will loop around and catch up to you, even if you both start at different points. This meeting point is your signal that the loop exists. Time and space complexity. The space complexity is O1 and time complexity is On. Time complexity because in the worst case the fast pointer will traverse each node once or twice. And space complexity O1 because no extra memory is used, only 2 pointers. This is what makes Floyd's algorithm so brilliant. It's simple, fast, and space efficient. Where it is used. This technique isn't just academic. It's used in real world systems like detecting infinite loops in software, ensuring data structures don't accidentally reference themselves, preventing transaction loops in blockchain, debugging pointer corruption issues in memory. Finding the start cycle. Bonus tip. If you want to find where the cycle starts, do this after detecting the loop. Keep the pointer at the meeting point, move another pointer from the head of the list, move both the pointers one step at a time. The node where they meet is the start of the cycle. How cool is that? Elegant and efficient. Just the way we like it at Code Tech Chronicles. Let's put our skill to use with another challenge. Is a linked list a palindrome? Palindrome. The idea is to use 2 pointers, slow and fast. When the fast reaches the end, slow is in the middle, at the middle. Then you reverse the second half of the list and compare it to the first half. If they match, it's a palindrome. This can be done in O(n) time and O(1) space. If you reverse in place, it's a fantastic problem that tests your understanding of list traversal and manipulation. Next up, another favorite, merging two sorted linked lists. Here is the trick. Use a dummy node to start the new list. Then compare the head of both input list and always attach the smaller one to the merged list. When the one list runs out, just attach the remaining nodes of the other. Time complexity is On plus M, and this approach is widely used in merge sort, data streaming, and real-time feeds. Let's compare the two types of linked lists based on their different features. For directions, linked list is just one way because it only has next pointer. Double linked list has two directions. It's next and previous. Memory uses is less in linked list because it uses one pointer. Doubly linked list has more because it uses two pointer. Deletion needs access to previous node in singly linked list. Doubly linked list because it's easier with direct backward reference. Traversal is forward only in singly linked list. In doubly linked list, we can traverse both direction forward and backward. Use case of singly linked list is stack, queues, and simple task, while doubly linked list is like history, playlist, undo, redo actions. Pick the structure that best fits your use case. Simplicity and flexibility, your call. Alright, time to recap. Understand the node structures, pointers are everything, master core operations, insert, delete, reverse, and merge, learn Floyd's algorithm, it's efficient and elegant, practice real world problems like checking palindromes and merging lists, use platforms like LeetCode, HackerRank, and Code Studio. Linked lists are gateway to mastering previous pointers and memory. They are must know for coding, interviews, and system level development. Thanks for joining me on this deep dive on linked lists. If you learned something new today, don't forget to like, subscribe, and hit the bell icon. This is Code Tech Chronicles, and remember, small step, big impact. See you in the next video.